All right, I want to work through some other definitions and examples with you. So in the previous video, we talked about linear equations. And now I want to talk about a system of linear equations. Sometimes instead of saying all those words, we'll just say a linear system, but you understand. A system of linear equations, all it is it's a collection of one or more linear equations involving the same variables, usually x1 through xn. And when I say involving the same variables, it may be that some of the equations have, let's say, x2 and others don't. So it's perfectly fine if the coefficients on one variable are 0, but we're using the same variables. I'm not using, y1 through y3 in one equation and x1 through x3 in the other. All the equations are using the same variables. So here's some examples of linear systems that I just wanted to work through with you. So you can see these are linear equations. I've gone ahead and written them all nice and neat, where you have the variables on the left and the constants on the right. It doesn't have to be that way. You may have to rearrange things in your problem, but here's a classic linear system. I wanted to make sure that we're comfortable naming these things. This is a linear system that has two equations, and you can see that immediately, right? There's one equation, two equations, and then we often care about how many unknowns are there, how many variables. Two equations, two unknowns. When people say two unknowns, i.e. we mean variables. It doesn't matter how you say it, but that's pretty common to refer to them as unknowns. So here's another linear system. By the way, I've gone ahead and put these nice curly brackets on my systems because I like to, but your book and a lot of the practical problems that you solve may not actually have these. It's perfectly fine if there's no curly bracket on the right. It's still a linear system. So this one, there's really not that much interesting to notice. I guess I made a coefficient of pi. Certainly the coefficients don't have to be integers. Sometimes we never see like root 2s or pi's or e's as our coefficient. They certainly don't have to always be just 1, 2, 3, 4, 5, 6, 7, so on and so forth. So this is a linear system, and it has 3 equations. You can see that. And then we're often interested in the unknowns as well, and you can see that there's 3 equations, 3 unknowns. Here's another linear system. This linear system has 2 equations and 3 unknowns. So there's actually more variables than there are equations, and we're going to learn that has some interesting implications. Now, I have just a quick question for you to think about before we go on. My question is, what if I was to take this x3, and what if, here, let's actually use white. What if I was to take this x3 for a minute, and I'm going to make it x to the 4th now. Is this a viable linear system? Because we said the same variables need to be used, and there's an x to the 4th here, and not in any of those. Is that okay? And the answer is yes, it's perfectly fine. You do have an x to the 4th here. It's just 0x to the 4th, and there's a 0x to the 4th there, so on and so forth. So just to point out, it may be that one variable lives in only one equation and not the others. No problem. We're good to go. All right, well, let's look at another series of definitions. These are all just vocabulary that you're going to need to know. None of it is particularly surprising or sort of counterintuitive, but these are the words we're going to be using throughout the course. So a solution of a linear system, a solution, it's a list of numbers that makes each equation true when you plug in S1 for X1 and S2 for X2 and so on and so forth. So the list of numbers is is in the same order as your variables. So it's you're saying that's what X1 needs to be, that's what X2 needs to be, that's what Xn needs to be. That's a solution, and it makes each equation true when you plug it in. So the set of all possible solutions to a linear system, it's called the solution set. And this is really an important one in 3. You can have different linear systems. I'm going to actually insert the word different. These are not the same equation, different equations, but they're called equivalent. So different systems are called equivalent if they have the same solution set. And that's going to come up in a little bit. We're going to learn how to sort of introduce equivalent linear systems. So, for example, let's say that our solution set to a system of equations is 1, 2. So we have two variables, and the first variable needs to be 1, the second needs to be 2, and that's the only solution. Then any two system of equations with that as its solution, I don't care what the equations look like, they're equivalent if they both have that as their solution set. We'll see more examples soon, so I'll say no more. Finally, two words that you're going to see throughout the course: a linear system is called consistent if it has at least one solution. You know what? Let's go the other way. Let's highlight the word that we care about. So consistent if it has at least one solution in its solution set, and it's inconsistent. A linear system is inconsistent if it has no solutions. So consistent means there's at least one solution. Inconsistent means no solutions. Okay, that's a lot of words, but I'm really not saying very much. I'm describing to you solutions of linear systems, no problem. We call all the solutions the solution set, no problem. Probably the most important sort of remark here is that different systems with the same solution set are called equivalent. Maybe we'll underline the same solution set there. So same solution set means your equivalent systems. And then consistent means there's at least one solution, and inconsistent means there are no solutions. So we'll stop this video here, and we're going to go on and do some examples in the next video.